All right, so my name is Saeed, and my partner Wook and I will be talking about feature denoising for improving adversarial robustness. So in this presentation, we'll discuss the problem description and what the authors are trying to solve, the solution that they propose, the experiments and results that they get, and conclusion, and then we'll go discuss the pros and cons and go to a Q&A session. So what is the problem? So as we know, perturbations add noise to an image, which can lead to noise in the feature maps used by the network. This changes the semantically important regions. So if you look at the top of the image here, this is a clean image, and this is the feature map generated from one of the ResNet layers. And as you can see, the focus here is right here on the clock. But on an adversarial image, there's a lot more regions that are activated in the activation map, in the feature map. And this can lead to the network learning on unimportant objects or areas within the image. So the authors propose a two-step solution. First is to denoise the feature maps by adding denoising blocks in between ResNet layers. And the second is to train networks on adversarial examples to reduce the feature map noise. So this is their denoising block structure. You have a denoising operation followed by the input to the feature map. Input is a feature map from a previous convolutional layer. Then a denoising operation is performed, and we'll discuss several operations that they test. Then the one-by-one convolution is used to normalize the feature map. And then the feature map is combined, or the denoise feature map is combined with the original feature map. And the output is sent to the next ResNet layer. So when designing this, they decided to test how important each feature was. When they removed the one-by-one convolution, the accuracy of the model was reduced drastically. This kind of indicates that the denoising by itself isn't impactful for improving the robustness. And when they remove the residual connection, the loss function refuses to decrease. So it's important that for the residual, or for the denoising block to work, you need the residual connection and the one-by-one convolution. So as we can see, if we look here, the first column is the perturbated images, and the second column is the feature map of those perturbated images. And as you can see, again, there's a lot of regions that are activated which are not related to the object. And then the third column here is the denoised feature maps. As you can see, it refocuses the feature map to one specific area. However, one downside is that if you look here, there are a lot more pixels that have higher intensity. And as a result of the denoising, the the intensities are reduced, which can also affect the model. Maybe the model won't learn certain features of the object as well as they should have. And now we'll talk about the different denoising operations.
So we'll be talking about 4 different noising operations that they implemented with a total of 6 implementation. The first type that they implemented was a non-local mean. So for the non-local mean, Cx is a normalization function, while fxi and f function is a feature weighting function. I and j refers to spatial location on the feature map, and L is referring to all the spatial location in the image. Yi is the feature map output for that specific location. So the Gaussian implementation, the weight function is equal to this, and the normalization function is equal to the summation of the weight function. And the 2 additional embeddings are theta x and phi x, which are chained through a 1-by-1 convolution, where theta xi is equal to the weight theta xi, and phi xj is equal to the weight phi xj, while d is the number of filter is in the feature map. If we look at the previous equation, we find that f over c is similar to a softmax equation. So the dot product implementation, the weight function is equal to xi transpose xj, while the normalization function is equal to cx is equal to n, where n is the number of pixels in x. And as you can see by the equation display, it requires a lot less parameters than the Gaussian version. The second implementation is the bilateral filter. The bilateral filter is the same as the non-local mean, except for the fact that it looks at the local region omega. The dot product can the dot product and the Gaussian implementation can be used here as well. The third denoising operator that we're looking at is the mean filter. It's a average pooling. It's a filter with an average pooling with a stride of 1, and it's the simplest form of denoising. It reduces the noise of the image, but it also smooths the structure of the image. And the last denoising operator that we looked at this paper is the median filter. The median filter is performed on the local region omega, and is performed on each channel separately. It's good at removing salt and pepper noise and any other type of noise that produce an outlier.
So for adversarial training, they generated adversarial examples with PGD. For each mini batch of images, they perform the PGD attack, and D is performed on perturbated images and the weights are updated. This drastically increases the runtime because they're performing PGD with 30 iterations before updating the model. And this is for each batch of images. So they train ResNet 101 and ResNet 152 as baseline models. These are trained without denoising blocks. And then a ResNet 152 model is trained with 4 denoising blocks. And they use non-local means with the Gaussian non-local means denoising operator. So in experiments, they also use PGD on ImageNet to attack the models. Iterations range anywhere from 10 to 2000. So as we see in this figure, the baseline ResNet 101 actually is 49.7% accurate against the 10 iteration PGD attack. The 152 is 52.5%, and the ResNet 152 with the 4 denoising blocks is 55.7%. As the iterations increase to 2000, their models show to be pretty robust, even with a 2000 iteration attack, which is significantly altering the images. The models are still about 40% robust. Another point is that while the ResNet 152 with the denoising blocks performs the best, it seems that most of the improvement is from adversarial training. The denoising ResNet 152 only performs about 3 to 4% better than the baseline ResNet 152. So they also tested the denoising blocks on non-adversarial networks, and they found that denoising blocks do not affect accuracy against non-adversarial images, and adversarial training affects the accuracy on non-adversarial images. So looking at the table here, the ResNet 152 model with no denoising blocks and no adversarial training, scores 78.91% on ImageNet. But if we add 4 denoising blocks to Resident 152, but still with regular training, the accuracy doesn't improve at all. It does, but negligible. But if we adversarial train a baseline Resident 152 and test on clean images, the accuracy drops from 78 to 62%. And if we again add 4 denoising blocks with adversarial training, the accuracy increases slightly. Denoised, and then they tested the different denoising operations against clean images. And they found that the denoising operations all have similar performance on clean images. So again, with the baseline Resident 152 with no denoising blocks, again, 78%. And then they add a bottleneck type of block, which only a 0.13% increase. Mean filter, again, is negligible increase, again, with the median filter as well. And both types of Gaussians, each denoising filter doesn't seem to improve the accuracy on clean images. And now we'll talk about the denoising operators again.
So to compare the denoising so for the comparison of the denoising operator, they compared it against the adversarial trained Resnet 152, no denoising block and a bottleneck block. So the no denoising block is just using the 1x1 normalization block, while the bottleneck block refers to the bottleneck block designed by He et al. And they use 4 blocks for ResNet 152. So if you look at this image, we find that the baseline model performed the worse. At 10 iteration, they found it 52.5%. And at 100 iteration, it was 41.7. The one that performed the best was the non-local Gaussian, which had the peak accuracy at 55.7 at 10 iteration, at worst at 45.5. But if you look here, the dot product version, while requiring less parameters, only had a slight dip when as compared to the Gaussian version. So the next comparison they did was a black box attack. So the evaluation criteria that they used was to pull all the black box attacks that they use and determine if the misclassification occurs. So they used the 5 best attack from IPS 2017 CAD competition. So when compared to the winner of that competition, it only had 0.044% when comparing all five attacks. But when they did 3 or under, it had 13.4. So as we saw before, the best filter that they used was a non-local Gaussian that had 46.4% accuracy. But when we look at just the normalization block, it's only a slight 2% increase compared to that, and the dot product was only a dip of 0.22% while having less parameters. They tried using a denoising block for all of the layer, and they found that it had an accuracy of 49.5%. So in conclusion, they show that the denoising of the feature map will improve the robustness of the model. They propose a new architecture style that include a denoising block to include the robustness of the model. And their proposed model has significant improvement against adversarial attack. The strength of the paper was that It showed a significant improvement against adversarial attack. They implemented a new architecture to improve the robustness of the network. It stays robust against a 20,000 iteration PGD attack. They showed that the denoising block did not significantly reduce the performance against clean image. And Saeed will go over the weakness.
So for weaknesses, they don't really have a metric on the loss of feature detail in the feature map. They don't really explore why denoising blocks are effective, and they don't test against other white box attacks. And they also only look at one architecture.